Okay, is this working here? Can everyone hear me? Okay. Yes? All right. Hi. So thank you very much for coming. We're very excited to have you here. I thought it might be a nice thing to do to start off talking a little bit about how you became interested in biology and then evolution. And when it occurred to you, as it did to me, that this very powerful idea is something central to shaping biological diversity.
The very powerful idea you refer to didn't really resonate with me until I was an undergraduate. So I got into biology more or less by accident. And then only when I became an undergraduate, I suppose in my second year, I started to get really, really excited about the Darwinian idea. Because, as you said yourself, it is the explanation for us, for all living creatures, for everything, I venture, in the universe which is complex. Because the world of physics is relatively simple. It's very difficult to understand, but it's not complicated. It's not complex. Complexity pretty much means biology, or the artifacts of biology. And on this planet, the only way we know for complexity of that sort to arise is evolution by natural selection. And I would conjecture it's the only way that it happens in the entire universe, but of course I can't prove that. It is therefore enormously exciting, enormously important, because it is utterly shattering to the imagination to think of what has happened on this planet. Instead of just being rock and water and sand and ice and the sorts of things which are on rocky planets all over the universe, on this planet, and possibly some others, on this planet we have organized complexity on a stupefying scale. Just to look at a single cell of a living creature, a single cell of a bacterium, and it blows your mind to think how complicated it is. And we are many, many orders of magnitude more complicated than that. And the Darwinian process is the process which has given rise to that complexity, including us, with our nervous systems, our brains, which are so highly developed that we have finally become capable of understanding the process that gave rise to us.
Wonderful. I think for a lot of people, it's very difficult to believe that the complexity comes from random physical forces. And I remember reading in The Blind Watchmaker an analogy you had about a primitive person walking along a beach, looking at the organization of the sand and the rocks. You see that the bigger rocks are toward the water, and the finer sands and pebbles are further up. And sometimes there's a line of garbage where I grew up. But so you might be tempted to think that that the creator is organized and tidy and likes to have things in this way. But we know now that the creation of those patterns of organization from disorder is created by wave action you describe in the book. So how is it that that this process, in that way, I think it's very easy for people to understand. What's the central thing that people need to understand to understand how human beings and the complexity that we sort of entail came to be?
Well, I think we have to be very careful when we use a word like random, because you just used the word random, by which you meant undirected, by which you meant not steered by any kind of conscious, deliberate design. But of course, if it were random in the sense of taking a whole lot of bits and shaking them up at random and seeing if they fell into place, it very much is not random in that sense. The waves producing ripples of sand or garbage on the shore might be, in a sense, random in that sense. But natural selection is a non-random process in the sense that it is cumulative over many generations of the waves shuffling the sand grains process. The waves shuffling the sand grains you could think of as a kind of one generation random process. But natural selection cascades those processes into many succeeding generations, where each one is selected so that it's a little bit better than the one before, where better is defined simply as better at surviving. And once you've got that, and it can only come about through the existence of something equivalent to a genetics, a self-replicating, a self-copying process, once you've got that, then cumulative, non-random survival over many cumulative generations can give rise to the prodigious complexity that so impresses us.
Another example that you use, the idea that randomness is involved in this process that creates diversity and complexity seems counterintuitive. And the wonderful example that you use is basically a sort of thorn in the eye of people who say, well, you know, randomness, you could write all the complete works of Shakespeare, you have enough monkeys bashing away at a typewriter randomly. But as you pointed out, the selection doesn't work that way. It actually preserves the beneficial mutations when they do come up. And so there's the example where you have the phrase from Shakespeare, methinks it like a weasel. And if you wait and randomly bash to try to get that sentence, it's very improbable statistically. But if you preserve, and I think the example from your book was your son randomly bashing away, as soon as he hit a letter that was correct, we preserve it and go on. It only took about 40 generations, right?
That's right. I mean, that's the key point, that the monkeys bashing away at a typewriter would take almost forever to produce even a single phrase of Shakespeare. But if you have a sort of ratcheting process such that each generation breeds the following generation, and of the offspring produced, the ones that are most perfect, in this case most resemble the target phrase, are the ones that you breed from in the next generation, then it only takes about 40 generations to produce the phrase that I chose, which was Shakespeare's methinks it is like a weasel. That's just a very short phrase. Now that, of course, is a highly artificial example because it is aiming at a particular target,
right,
which natural selection doesn't do. Or if it does aim at a target, the target is an extremely general one, which is simply survival. So there's no sense in which there's a kind of distant target on the horizon, like a phrase of Shakespeare. There was never the human frame, the human body, as a distant target of evolution. A lot of people think that somehow was the case. Absolutely not. There are millions of independent results of natural selection. None of them could ever be called a target. The only criterion is survival, strictly gene survival.
So this idea of genes as being the unit of selection is something that you've championed throughout your career. What implications do you think that has for the study of evolutionary diversity?
Well, it's really a way of defining how the process has to be. This process of non-random survival, non-random ratcheting, depends upon there being something that is capable of surviving. And genes are the only things in the biological sphere which are capable of surviving in the sense required, which is that they make accurate copies of themselves, very, very accurate copies of themselves, but not quite perfectly accurate. There are occasional mistakes. And so, as you know, it's these occasional mistakes, these random mutations, which give rise to the diversity, which can lead to improvement. But nothing else in the hierarchy of biological organization has this property of being potentially immortal. Genes do, genetic information, not the genes themselves. I mean, the physical matter of DNA decays very rapidly, but the information contained in the sequence of bases in DNA is potentially immortal. It can go on for hundreds of millions of years. Mostly it doesn't, but potentially it can. And therefore there is a very real difference between those stretches of DNA which do go on for a very long time and those which don't. And that is natural selection. And nothing else in the hierarchy of life has that property of potentially going on forever, which therefore makes the difference between those that do go on forever and those that fail because they don't cut the mustard.
So one of the wonderful analogies that we have for replicating systems like that that is brought up in many of your works are, for example, replicating clay crystals. There are things that have a property of replication where their abundance is dictated by their fidelity of copying and the rate at which they do that. And that's just simply what happens, right? And the way that a certain type of clay crystal can predominate and sort of end up taking over a bank, if you will, of a river is a very similar process in this way, with the exception that the replication machinery there is not very sophisticated.
I mean, crystals are a very nice case because crystals grow by atoms getting out of solution and joining up in just the correct places in the crystal that's already there. And so whatever structure is already there gets replicated. However, in order to be an interesting replicator, by interesting I mean biologically interesting, Darwinianly interesting, there has to be a possibility for variation. It's not enough to say the atmosphere is full of oxygen atoms, and so you might as well talk about the selfish oxygen atom as the selfish gene. There has to be a sense in which a pattern or something is replicated with variation, with the possibility of error, the equivalent of mutation, such that some variants, some products of error, some variants are more likely to survive than others. And that, of course, DNA has par excellence. The clay crystals you're talking about, according to the Scottish chemist Graham Cairns-Smith, have a kind of rudimentary version of that, because a crystal that for some reason develops a glitch, there's a mistake in the way in which the atoms fall onto the existing crystal, and if that mistake is then repeated forever after or until there's another mistake, that does have kind of a rudimentary version of the property. But it doesn't become biologically interesting until there's a population of alternative varieties such that there can be non-random success, non-random survival of some variants rather than other variants. Cairns-Smith actually went so far as to suggest that clay crystals, inorganic clay crystals, could have been the forerunner of life, because he's writing books about the origin of life, correctly recognized that the key stage in the origin of life would have to have been, we don't know what it was, but it would have to have been the origin of the first self-replicating, self-copying entity in the sense in which I've just said. DNA cannot have been that original replicator, because DNA is what Cairns-Smith called a high-tech replicator. It needs too much infrastructure to copy itself. So he tried to think of what might have gone before the eventual takeover, as he put it, by DNA. So he saw DNA as a sort of late usurper of the role of self-replicator, of genetic molecule. And he saw as the predecessor of DNA, he saw inorganic clay crystals. And he makes a kind of reasonably plausible case, but it's not a case that's widely accepted by other researchers on the origin of life.
Well, this is fascinating, because it seems then that there are intermediate molecules that are maybe on the way to becoming full-blown life, like replicators in the sense of that create life.
Yes, I mean, nowadays it's more fashionable to talk about RNA as being the possible intermediate in that sense. And I think it's a very interesting idea, because if you ask the question, why, in what sense is DNA too much of a high-tech replicator? One crucial point is that DNA requires protein enzymes in order to replicate itself. And the enzymes that are needed to help DNA to replicate itself have to be made under the tutelage of DNA itself. So there's a catch-22, you can't have one without the other. Enzymes are mostly proteins in the world in which we know. And enzymes have their catalytic properties because of their physical shape. And the physical shape of a protein molecule, a globular protein, is determined by the one-dimensional order of amino acids, which cause it to coil up into a tight knot shape. And the shape of the coil, the shape of the knot in which it falls, is determined by the one-dimensional sequence of amino acids, which in turn is determined by the one-dimensional sequence of DNA bases. Now, it's the three-dimensional shape of the protein molecule that gives it its catalytic, its enzymic properties. RNA has some of the qualities of an enzyme. It can do the same job as protein, to coil up into shapes which have a catalytic function. And RNA also has, not so good as DNA, but it has some of the properties of DNA as a replicator. So modern life on this planet is a partnership between DNA, which is a brilliant replicator, but a hopeless enzyme, and protein, which is a brilliant enzyme, but a hopeless replicator. And they therefore need to be in partnership together. But RNA is a moderately good replicator and a moderately good enzyme. And therefore the thought is that before the partnership between DNA and protein got going, RNA could have stood on the stage alone, doing both jobs. And then you got a kind of bifurcation of the functions later. So the original thinking of Cairn Smith is still there, but instead of having inorganic crystals as the forerunner, we have RNA as the suggested forerunner. And that's a currently very fashionable idea.
The self-catalytic activity of RNA is fascinating. And that makes it, this idea of the RNA world that was a pre-DNA biology. One of the things we spoke about earlier at eating was education and talking about evolution and having people appreciate that from an early age, because it does sort of form the scaffolding upon which you can hang a lot of facts in biology.
When I learned biology, I learned evolution sort of last. I mean, first of all, I learned about cells and cellular chemistry and things like that. How on earth can you appreciate cells and cellular chemistry without knowing what it's all for? I mean, how can you even begin to learn biology without starting off by an idea of what it's all for, where it all comes from, what the history of it is? And so I would turn the sort of textbook order in which biology is taught, where very often evolution is left to the last chapter, make it the first chapter, and teach it young, because it's not actually that difficult to understand.
So over the years, I've had an ability to, an opportunity to appreciate the ideas in your books and to understand that not teaching evolution early has pretty big consequences. So one of the things I remember reading as a graduate student was they had finished the crystal structure of the protein that does a translation of genes into proteins. And it is made up of many, many globular proteins, and it's a very complicated structure. It also has catalytic RNAs that are part of it. And the big question was, is it the catalytic RNAs that do the translation, that turn the DNA into protein, or is it the RNA? The proteins are RNA, And in the paper where they describe the crystal structure, and they say the catalytic RNA is the actual thing that connects together the amino acids during translation. And this is in support of the RNA world theory. It was not mentioned at all in the paper.
Interesting, yeah.
And that's the kind of thing is where we become so specialized in these different areas, but evolution seems to be one thing that can tie it together.
Yeah, so they just don't make that connection.
Right. Well, how early should we start teaching people about evolution?
About 6 or 7, I should think.
Is that a good age?
Well, I mean, you could certainly teach about evolutionary history at a very, very young age, because you can ask a child, you say, well, you know who your parents were, they're your grandparents, and they must have had grandparents, and you can kind of go back, and ask the child to imagine what their 10,000 greats-grandfather looked like, and then their million greats-grandfather looked like, and you can gradually show the child a picture of what your million greats-grandfather looked like, or your 200 million greats-grandfather, who would have been some sort of a fish. That's easy enough to get across. But then you need to point out that it's actually not. There's something a little bit counterintuitive here, because there was never a sudden change from a fish into something that wasn't a fish. If you were to, you could easily ask a child to imagine getting your father, his or mother, her mother, going back, line them up in a great big line, stretching for thousands of miles, and you walk along this line, going back to the fish, to the 200 million great-grandparent. At no point ever in that line would you come across an individual who belonged to a different species from its parents or its children. So at every single stage, the successive members of the chain would be all but identical to the one before and the one after, as identical as parents and children ever are. And yet, because there's such an enormous number of generations, imperceptibly, by gradual degrees, as you walk backwards in time, you would make the whole gamut of change from human to fish, while there would never be a perceptible change in any one generation at all. And people might find that counterintuitive until you point out to them, children might find it counterintuitive until you point out, you were once a baby, then you became a toddler, and then you became what you are now. But there never was a moment when you woke up and suddenly ceased to be a baby and became a toddler. There never will be a moment when you cease to be a child and become a teenager. There never will be a moment when you cease to be a teenager and become an adult. There'll be your 18th birthday when you're recognized by law as an adult. But that, of course, means nothing. You don't suddenly wake up and say, oh, I'm an adult, finally. And yet, we change through life. The change is too slow to be perceptible, just as the movement of the hour hand of a watch is too slow to be perceptible. But if you come back and look at it every now and again, you see that it's moved. But any of that should be easy to get across to a 6-year-old.
And we have wonderful analogies for this idea of continuity and deep time that we can reference. Like the development of a human being, you spoke then that there's a continuity, but there's change there. The concept of how much time has elapsed, though, for these things to happen. Why is it so hard for people to appreciate that?
Well, it's so off the scale with respect to any time that we're used to dealing with. I mean, our lifespans are measured in decades, and we are asked to. I mean, even studying history, we can cope with centuries all right, but by the time we get back to the ancient Egyptians or the Sumerians or the Babylonians, we kind of get a tingling up the spine. This is sort of lost in the mists of deep, distant time. It's nothing compared to evolutionary time. And we've got to start learning to deal with not just millions of years, but hundreds of millions of years. And the human mind is not evolved to cope with time on that sort of scale. We can do it by analogy, and as you've said, I mean, the analogy of the developmental time of a human, you can analogize it to a clock. That's one way of doing it, and you know that if you say that since the origin of life, if it's one 24-hour clock, what does it tell you? Somebody probably knows the answer. Humanity came on the scene 5 minutes before midnight or something of that sort. A favourite one of mine, which is not my own, one that I've adopted, is you hold out your arm and you reckon the origin of life is where your microphone is. And the present is out at the tip of your fingers. And it's all bacteria out to about there. And the dinosaurs are about there. Human fossils, people like Lucy, come at about where near the tip of your fingernail. And the whole of human history, recorded human history, the Egyptians, the Babylonians, the Hebrews, the Romans, the Greeks, the Middle Ages, the whole of recorded human history falls as the dust from one stroke of the nail file.
That is a beautiful analogy, thank you. This idea of, I think this is what makes evolution so difficult for so many people.
That's one of the things, the time span is one.
The time span. Another, a wonderful analogy that you use. So everyone knows a Chihuahua and a Great Dane, right? You know, that these are animals that are derived from a wolf. And one of the great analogies that we use in the Introduction Evolution course that I teach here is from one of your books. I think it's Blind Watchmaker. We say, if you go from a wolf to a Chihuahua, and that's one human step. That's about 2,000 years of human artificial selection, not natural selection. But just to get an idea, that's kind of a radical change, right? Like this wolf to a little thing, a Great Dane. And if that's 2,000 years, you ask us to imagine, what would it be to walk through the history of life? How many steps would you have to take? And anyone have any ideas? So people in the class can't answer. You would have to walk from London to Cairo, right? And this is just something that I can't imagine doing that.
I think the point there is that the difference between a wolf and a Chihuahua is a pretty substantial difference. And if that can be achieved in, what did you say, a couple of paces?
One step.
One step. If that can be achieved in one step, wolf to Chihuahua, how much could be achieved on the long slog from London to Cairo? Of course, as you said, the wolf to Chihuahua is artificial selection, not natural selection. But there's really no difference. I mean, it's just differential survival of genetic types. So whether it's artificial selection or natural selection shows the power of the principle of selection, what can be achieved by selection, going from wolf to Chihuahua in one step, where the whole of evolution is the march from England to Cairo.
So if we can place ourselves in that situation by way of these analogies, why do you think it continues to be so difficult for people to appreciate that we have I struggle myself in my own life. I teach this to students, and I have spoken about it with my family, for example. But my mother says, the human heart is made of the same material as a chimpanzee heart. I don't see the difference. I don't see what's going on. I don't see what the big deal is. Somehow we're made of the same compounds or materials. But what I took away from, I just was left with this, essentially, that the reason that the heart in me has the same shape, the morphology, and it works the same as in my mother's, because I inherited it from her. And the reason a chimpanzee heart beats the same as a human heart, similarly, not the same, right, is because we inherited it from actually the same grandmother. Just as you said in this beautiful march of life, that individual existed at one time as a common ancestor. In this great chain of unbroken continuation from a fish to a person, what does a genome look like? How much does it change from generation to generation? Is it a very radical change, or is it also gradual?
In the short term, it's not a radical change. It's just changes in the actual bases in particular genes. There are, of course, larger changes because numbers of chromosomes change. The size of the genome is different in different lineages, and therefore, at some point, the genome does get larger or smaller. It gets larger by gene duplication. Whole chunks of genome can get split off and parked somewhere else in the genome, and that's how the genome can get larger. And when that happens, the different chunks that once upon a time were replicas of each other can then start evolving in different directions, doing different jobs. So, for example, there are a number of different hemoglobin molecules which clearly have the same ancestry. They're all descended from a common molecular ancestor. They split apart into different parts of the genome and went their separate ways in different parts of the genome doing different jobs. And that's a model for what happens over and over again, and that's how the genome becomes bigger and more complicated. But going back to the hearts, I think I ought to qualify what I said when I said that as you go back in time, There's never a moment when there's a radical step. You do have to remember that I mean, we have a 4-chambered heart, and fish have a 2-chambered heart. So at some point there must have been, I mean, it's not easy to imagine a 2 1/4 chambered heart. And so there must be a certain number of major steps of that type. Another example would be snakes have an enormous number of vertebrae, but different species of snakes, and all snakes have many more vertebrae than we do, but different species of snakes have different numbers of vertebrae. And you can't imagine a snake that has that goes from 100 vertebrae to 101 vertebrae by going through a stage of 100.5 vertebrae. So there must have been a mutant that had at least a whole number increase in the number of vertebrae at some stage in evolution, maybe even more. That's not actually as difficult to imagine as you might think, because although each vertebra is complicated, it's got the vertebral bird itself, it's got ribs, it's got muscles that go with segmental muscles, nerves, blood vessels, all built on this segmented repeat pattern. But because the pattern is there, and because the genome already has the capacity to build a segment, building a second segment is a very easy thing to do. And so, and nowadays the embryology of that is very well understood, so-called Hox genes. There are fish that have 4 eyes instead of the usual 2 eyes. They have the usual 2 eyes looking out that way, the way a normal fish does, and they have a couple more eyes looking downwards. And we can conjecture that this fish suffers from predation, predators coming from below, and so it maybe benefits by having this extra pair of eyes looking downwards. But the evolution of the extra pair of eyes, I don't think it would be reasonable to suggest that it went through a stage of having 2.1 eyes, 2.2 eyes, 2.3 eyes, etc. It probably happened in a single step. And again, that's not difficult to imagine, because the embryological and genetic machinery for making an eye is already there. And so probably all that had to happen was the duplication of a Hox gene that said build 2 eyes instead of 1, using all the same machinery as you used to build it before. So that I wanted to put that in as a kind of qualification of that ultra-gradualistic point.
This idea that there are gene duplications, for example, at the level of the genome, which is in a way, this is the blueprint of how to make a human being, or how to make a cabbage or an octopus, right? Rudy Raff has a wonderful analogy. He says, you know, if this manuscript is the thing that we need to modify to improve, you know, it's kind of like trying to improve, evolution is like trying to improve an engine while it's still running. You know, it has to perform because you want to tinker. So the question is, how can you do that? It seems very difficult. Yeah. And one way to do that is to duplicate a gene. So as you know, we have hemoglobin binds oxygen, there's alpha globin, beta globin, they have origin as genes that duplicated and diverged in function, and now they work together to carry oxygen. That's exactly the kind of thing that you see happening all over the place. Now that we've been able to sequence genomes, we see massive evidence for gene duplication, and this allows one to tinker, essentially, while still having the engine running.
It's not quite as bad as still having the engine running, of course, because evolution is not a change of one adult body into another adult body. It goes back to a single-celled egg first, and so the new embryo develops. And the engine, in a sense, stops in each generation. But that's a quibble. I mean, the analogy is a very good one.
So then, if this process of the replicators and of the information being accumulated via natural selection in this cumulative selection fashion, what does that say about the probability or the possibility of life on other planets? Would it have a similar character? Would it have to be a replicator, you think, as well to be life?
Yes. We've only got a single sample of life to look at, the one that we have on this planet. And every living thing that's ever been looked at on this planet is astonishingly the same. At the machine code level, we all run the same machine code. It's not as though some creatures are IBM PCs and some are Macs. I mean, they're all the same. But it's all kind of frills on the surface that makes the difference between them. If we start moving into other planets, to exobiology, then we have no idea. We can only guess. We can make informed guesses as to how similar it would have to be. Would it, I mean, you asked, would there have to be something equivalent to replicators, something equivalent to genes? My very strong guess, I put my shirt on the answer being yes. That whatever else you can say about life elsewhere in the universe, if there is life elsewhere in the universe, and I bet there is, it's got to have a genetics. I suspect it's got to be digital genetics, not analog genetics. DNA is digital. It's not binary, it's quaternary, but it is digital. And that gives it the extreme high fidelity which seems to be required in order for natural selection to work. So let's put our shirt on digital genetics. Does it have to be DNA? Well, I doubt it. I don't know enough chemistry to be able to say, but my guess is there probably are other kinds of molecules that could do the job, although I don't know that for certain, and I would throw it out as a challenge to chemists here to try to imagine an alternative to DNA, an alternative chemical system which could do the job of providing a replicator plus a great variety of coded information. Would there have to be something like protein, or at least enzymes? I think there probably would. I mean, I think there's got to be something capable of. No, maybe that's being too unimaginative. Maybe a chemist could produce imaginative schemes that didn't involve protein. You can go on asking these questions. Would there have to be multicellularity? I mean, large creatures on our planet are all made of lots and lots of cells, and all the cells have the same basic plan. We don't know of a way of becoming large other than making lots and lots of cells, but is that inevitable? Is that something that has to be true of all life, or is that something that just happens to be true of life on this planet? I don't know the answer to that question. Does there have to be something equivalent to sex? Well, no, because not every creature on this planet has sex. You can go on asking these questions where, in every case, what you're asking is, how much of what we know about our kind of life had to be so because there's no other way of doing it, and how much just happens to be so on this planet? Does it have to be so that you get a life cycle in which in every generation it returns to something like a single cell, something very small and simple? Or could you imagine a life form which evolved by just changing, rather like getting a bit of clay and kneading it, molding it into shape? My guess is it has to be something like what we have, which is a return to a single cell origin in every generation. And again, maybe I'm being too unimaginative. The day when we first discover another life form on another planet will be, if I'm still alive, it would be the most exciting day of my life. It would be the most astonishing thing to live through. I fear it's very unlikely. I believe there is life on other planets, but the reason for that belief is the extraordinarily large number of planets that there are available. But the trouble is that the other side of that is that the universe being so huge, the islands of life dotted around through the universe may be so spread out, so sparse, that although they all have life, these islands, they may be so widely separated from each other that they never meet, never